Okay, I just started the recording. So, first question. Omar, you're muted. Okay.
Yes. Good morning, Professor. Could you go over stereo-specific versus selective?
Um, just pay attention to those terms for now. I'm not going to specifically test on them, but just to touch base. Um, stereo selective means you have two stereoisomers you might get in a reaction, and one of them is preferred. Okay, so it doesn't give a random um, stereocenter. Could double bond or a chiral center. So stereoselective. Uh, one type of stereoselective is an antioselective, meaning it gives one enantiomer over the other. We'll only actually learn one reaction like that next semester. But it also could be referred to cis and trans. So you'll learn a reaction again next semester that has a high preference for giving cis, which is unusual. The eliminations are somewhat stereo selective for trans because it's more stable. Okay. Stereo specific has a broader meaning. I mean, not broader. It requires a pair of reactions, the best way to say it. So it takes the cis and makes one diastereomer, and it takes trans and makes the other diastereomer. Okay, so this is just terms I've introduced, but I don't test on vocabulary. It just encourages you to think about what's happening with stereoisomers. What are the consequences of doing a reaction in terms of cis and trans or diastereomers? Again, we're not going to deal that much with an antioselective reactions. They'll be mentioned. You'll learn one specifically next semester. Okay? Does that answer your question?
Yes, thank you.
Okay. User one, and I'm seeing only one real person here.
Hello, Professor. I was wondering, can you show us how we make a molecule anti-periplanar before we do the E2 reaction? And also, can you show us an energy diagram example that we might be asked to draw? Like when you say that, like labeled diagram?
Okay. Let's do one at a time, but yes. So I am going to give you the shortcut. Um, and then I'll explain it in a little bit more, maybe. We'll see how this goes. But let's say, just a minute. There we go. Okay, let's say we have this. I don't know why it labeled it that way. So let's say we have this diastereomer. Okay, so if the bromine is going down and toward you, and the methyl group is going away, back and away from you, or up and away from you, they are anti-periplanar. Okay,
So,
so go ahead.
so one of them has to be on the wedge, and one of them has to be on the dash. That's the only condition for E2.
Well, they're on the opposite side of the zigzag too.
And this is a condition for only E2, right?
Um, for eliminations, yes, for E2. So in this case, it can't eliminate in this rotamer, this conformation, because the hydrogen that you need, you can add it, but you don't need to have wedges all over the place. The hydrogen is not in the right location. The methyl is. Okay, so let's switch these. Okay, so now the hydrogen is the right location. And so if you do the elimination, the carbons that are in the plane of the paper, these five, won't really change much. The double bond will be formed by a loss of the hydrogen shown. And of course, you got to have your methyl group here. And that's the product. It was drawn representing what you need to do the elimination.
What if we just left the methyl on the wedge? Would that be wrong?
Yes, wedges make no sense on double bonds.
Oh, I see.
These carbons are all coplanar. What sense does a wedge make? So, it's one of those things that I really think I should take off for, but I usually don't, but don't push me. Yeah, it makes no sense. If they're flat, if it's in the plane of the paper, wedges make sense. Okay. So that's what I've just shown you is the reaction where the hydrogen is in the right place. And so I've given you kind of an easy question.
What if we were given a molecule that we had to change to anti?
Yeah, I'm getting there. I'm just kind of completing it. Yeah, I just want to make a complete reaction here. And now what about the other one? This one. Okay, now you got to do something. The shortcut, I'm going to give you the shortcut and then a more involved analysis. The shortcut is to say, well, it can't eliminate the way it is. So I can't get the same product, but there's only one other choice. The other choice is that one. It's got to rotate.
Professor, I'm confused, but we started with a dash and a wedge for this one, and isn't it already anti-periplanar?
The methyl is, you need the hydrogen to be anti-periplanar.
Um, can you show us like what that means?
Yeah, I'm going to go there, but this is a shortcut. So let me go through the logic again. I hate this. Let me go through the logic again. This is set up right. What does happen during the elimination is the hybridization of these two carbons change. They go from sp cubed tetrahedral to sp squared flat. Trigonal planar for the fancy word. They go flat. So as the elimination happens, the hydrogen that's behind the bromine here on the same carbon will move up. This methyl group will move down. And it'll end up planar, as we've already discussed, that the product is planar. Okay? So again, this one is straightforward. If you can see that the hydrogen is in the right place, you don't have to adjust anything. You just have to flatten it out. The bottom one, you can see it will not work. So you have to rotate it. But there's only one other choice for the product. So if you rotate this to put the hydrogen right and go through the full analysis, this is what you end up with. The only other choice. Okay, that's the shortcut. If you want to actually do it correctly in terms of analysis, let me move this over a little bit. Yeah, I hate the way it does it. Anyway. So I want to rotate it so the bromine is aligned correctly to this hydrogen. Okay? So if I rotate around this bond, let me see, how do I draw this? No, I hate these things. I think I can use this. Yeah, I'm trying to change it so it looks more, but I hope you get the idea. Sorry. That looks a little better. So I'm rotating it. So the way I'm going to rotate it is to put the bromine back here, the hydrogen up here, and the methyl here. Okay. And now the bromine is hashed going away. The hydrogen is solid hashed or solid wedged. It's coming toward. These are transdiaxial. In fact, if I just do this, it makes it look more like it. But this is somewhat artificial. So you do the elimination now. Um, this carbon flatten out with the methyl coming up. This flattens out with the methyl going down. And you end up where we did when we did the shortcut. Okay? So again, I normally would just ask you what the product is, but if I ask you to redraw it at some point, this is what you do. You simply rotate the bond. And you've got to remember that, it flattens out. The bromine is gone, the methyl goes down, so it's planar like this. The hydrogen is gone, the methyl comes up, it's planar like this. The top one gives you E, the bottom one gives you Z. Cis and trans not applying.
Thank you.
Okay? Yeah, that doesn't make it easy, but it is easier. And I gave you a shortcut, but you got to be careful with shortcuts. You got to think about it. Okay. Okay, next question.
Oh, I think you missed the energy diagrams.
Oh, energy diagrams. Well, no, I do one question at a time. So I want to save this. Give me a second. I didn't look. Port. No, I don't want a PDF. I want a CamDraw. It always use whatever you use last. Oh. Okay, let me do one other thing before we go on. If you have a bromine on a ring, And so you're going to do an E2 elimination with a ring. And you have this setting. It actually is a lot easier because you cannot rotate it to make it eliminate if it's not lined up. Now you have to worry about which chair, but you don't really quite need that in the analysis. So this bromine is towards you. You need a hydrogen going away because they have to be transdiaxial. Transdiaxial is just antiperiplanar in the context of a cyclohexane. Okay, so this bromine needs a hydrogen anti to it, trans to it. This hydrogen, not so much, it's cis. This hydrogen is in the right place. And so if you eliminate this, there is only one possibility at all. This is going to be highly stereo selective. And that's going to be the only product you see, which is the kind of chemistry we like. Okay. And now I'm going to get rid of that. Let me explain. I have to show the relative stereochemistry of these three carbons. To do that, I need the wedges. Okay? So I have a reason to use the wedges outside of any optical activity. When you use more than one wedge, the assumption is that it is not optically active, that it's racemic. So if the starting material is racemic, then I don't need this wedge anymore because there's no relative stereochemistry to see. Okay. Now, if I put this on an exam and you give me that for an answer, yeah, I might put the little red ink on it, but you get full credit. But the convention is that is not an optically active compound because I haven't clearly stated it. More than one wedge implies a racemic mixture without a statement to the contrary. Okay, so that's just the literature convention. I'm not testing on it. If you forget it, it won't hurt you, but I like to stick with the literature, with the publication, the conventions and publications. Okay? Okay, so I don't know who it was talking to me. Is there a reaction you'd like to pick for an energy diagram?
The most difficult one that you can think of putting on the exam.
Okay, SN1 or E1?
Both.
Yeah, I don't know. I may be interrupted and have to make this short. Okay, we got to vote for SN1. I'll go with that. I may have to cut this off and make it short. It's a complicated situation. I will make an announcement, but lecture on Tuesday will be recorded. It will not be live. I will post the recording and I will open a chat on Brightspace for any questions. An elderly member of my family having major surgery on Tuesday. And I was trying to figure out how to do lecture. It's just going to be the schedule is going to be too complicated. It's a 6-hour surgery.
Oh
So,
my God, I hope they feel better.
yeah, well, there's always a risk from major surgery, but most of the time it works out just fine. Okay, forgive me while I draw a little bit. Then I have to think about it a little bit. I'm actually drawing a chemical structure. It's just the easiest way to do it here. A little bit. Okay. So let's just keep it simple. Okay, I'm going to make a comment here about heat. Your textbook gives the implication that if you heat something, you'll get elimination. I'm sorry. T-butylbromide is a stable molecule. You can put it in a bottle, you can keep it, you can store it, you can use it whenever you want to. You need a little bit of heat to get this reaction going. Don't ever assume that heat means elimination. Okay? You don't want to heat it more than you have to, but you're going to have to heat it a little bit. Okay, so I'm going to take that out of here for now. So we don't really need it.
Question.
Yeah.
So is heat the same thing as warm then?
It's just a matter of, heat. I do warm only to offset what the textbook does. I mean, I don't know why they say it's going to bring elimination. I mean, there is a relationship, but they create a lot of confusion the way they address it. Okay, so this is the reaction we're going to do. Okay. I mean, okay, so the first step is ionization to the carbocation, which is a high energy intermediate, but it's an energy minimum, and then the product at the end. So if I ask to label it completely, that would go there. And I am going to stop at the product that still has that hydrogen attached. So let me show it explicitly. Okay, just to save complications, it's just easier to stop there. Okay, and we don't need any of this. Or maybe I should have left it there. Oh, I don't want the whole page. Stupid program. This program can be improved in so many ways. You can imagine organic chemistry drawing programs do not have a major market. Okay, and we all know what goes here, right in the middle.
The carbocation?
You got it. Prophetic, you can read my mind. Yeah, so now you need to tell me what's at the peaks too. So this, okay, follow along. This would be a partial bond. Oops, go away. So this would be a partial bond. The bond would be a little longer. These would be flattened out a little bit. And no, I'm not going to get picky about details of the drawing. Okay, I think that works. You would have D. If you type letters in the symbol font, you get the Greek letters. If you ever need that, lab report or something. Come on, come on. There you go. Okay, so that's the first intermediate. I mean, the first transition state. The second transition state's an awful lot like it. Um, But now the positive charge is developing on the oxygen, and the positive charge is diminishing on the carbon. Put them in here. Looks better. Okay. So if I just ask you to add all the structures, that's all you need. There are other things on here that are important. It should be easy for you to label if I ask you to. That's an activation energy. That is also an activation energy, but not one of much significance. Okay. You could label energy changes from here to the intermediate and from the intermediate to the end. That's not a common thing to do. So the only other really meaningful thing to do is to label this, and that would be delta G. And again, that activation energy is not really that important. These are the two important ones to label. That is just, yeah, okay. It's an activation energy, absolutely. If you were to label from this level to this level, that's the energy difference between the cation and the T-butyl bromide. You know, if you have a secondary cation, that would be much higher. If it were resonance stabilized, to be lower. I don't really judge whether you have the energy gaps realistic or not, just so you don't have them absurd. The overall reaction is favorable under the conditions, so it's exergonic or exothermic if you prefer, but exergonic is the better term. Okay, any questions?
I had a question about Hammond's
Yeah.
postulate here.
Yeah.
So since the first step is an endothermic step, that means according to Hammond's postulate, the first transition state is more similar to the intermediate. What does that really mean, though?
Okay. Well, hold it. You made you I lost track of what you were saying. Um, oh, the rate, you said the first step, which it is here, absolutely. But the better expression is the rate determining step. What is the slow step in the reaction? For example, if you're going to do an alcohol and protonate it and make the bromide via an SN1 reaction, the protonation doesn't matter. That's not the rate determining step. Okay, so it's the rate determining step. That's the way you should word it. Okay, so the Hammond's postulate goes back to a point when transition states really weren't known, and they had no way of calculating them. We can do that now, but the idea is that the positive charge on the T-butyl cation is significantly developed in the transition state. The transition state is closer in energy to the carbocation, so it's much more similar in properties than the starting material, which is far differ in energy. So Hammond's postulate focuses on what's the most similar to that transition state, and it would be that intermediate, and would be this transition state. And so the idea here is that the energy of this transition state, because it had a positive charge here, somewhat resembles the positive charge in the carbocation. And so if you have an intermediate that would make a better carbocation, that will be seen in the rate of the reaction. Just to put that to an example, if I put a phenyl group here, oops, phenyl, oh, come on. There we go. If I put a phenyl group here, And now this has a phenyl group. This is a phenyl group. I have made my intermediate more stable. Actually, let's do all of them. And so it's going to bring down these energy levels. Oops. Okay. And so now we expect a faster rate of reaction because my activation energy has been lowered by that amount. Okay, so that's the thinking of Hammond's postulate. Okay, let me continue with Hammond's postulate for SN2, just to compare and contrast, if you will.
Could you also show the how to draw the stereochemistry in the transition state of SN2?
You know, SN2, the
Yeah, the
inversion, you mean?
stereochemistry in the transition state.
Well, then it's just the inversion. Yeah, let me just draw an entire. Uh, Give me a pain in the butt. Oh, I should save this while I'm there. Port, chem draw.
Professor, before drawing this, how did you know that this was exothermic? Or will you just already give us the
You
curve?
know, reactions that are useful are all exothermic, right?
Okay.
Yeah, you can draw it for one that's not exothermic overall, but it mean it's not going to go very far, you know. And it sometimes might make sense to show that.
Oh, so you will already give us the curve. We will just have to predict the product and label the curve, right?
No, you'd have to draw everything. I'd give you a horizontal line and a vertical line as axes.
Oh, I see.
Easier to start over. Yeah. Okay, now you can have an SN2 reaction endothermic, but it's just not a useful reaction. So we focus on what actually is useful for something.
Dr. Hammond, how do we know if it's endothermic or exothermic? Or do we just assume it's always
Assume it's exothermic because that's what's going to be for a useful reaction.
assume it's exothermic
The overall reaction, yeah,
for SN2, but
for
not
any reaction. Yeah, we like reactions are useful for making things. Endothermic reactions, not so useful. I mean, there's no reason we can't talk about them, but they're just not very useful.
the example we just did for SN1 was endothermic, right?
The first step is endothermic, but the overall reaction is
Oh,
exothermic.
exothermic. Okay,
So if you're going to make a carbocation, yeah, it's going to be endothermic. There's no way to get around that.
okay, thank you so much.
Just to be complete. And now, I'm sorry. Maybe I should have done this ahead of time, or, I could try to find them, but if you watch me draw it, it gives you time to think. Okay, so now we have the bromine. Its bond is breaking. Let me draw it compatible. What's down there? Whoops, grabbed wrong. Oh, hold it. Oh no, that's what I want. I shrunk this down at one point. Put it back. Okay, I'm going to put the hydrogen down here. So here we have no stereocenter, but it doesn't really change much. You'd simply label it appropriately.
Like I saw somewhere that if you are starting with the R and R or S molecule, you should draw it the same way in the transition state.
Oh, absolutely.
That's
Absolutely.
more what I was asking.
Oh, okay, okay. Am I going to do this without making it too complicated? I'm going to do something highly unusual, put a fluorine there, just as a holder. Well, no, let's just make it R. The fluorine would work because the fluoride is so unreactive, but let's not get too exotic. Okay, so that we have a chiral center there. Okay, now let me think about this. Uh, You have to hold down two things to do this, and if you let the wrong one loose first, you lose it. So there's a hydrogen back here. Okay. So I'm going to change this completely around so that this is the same way. So that's the R group. Okay.
Is this SN2?
This is SN2. We did SN1. E1 and E2, would be very similar. You just have to keep track of things. I mean, okay. Who wanted to know about this? Is it good enough for you?
Yeah,
Um,
that was pretty good. Thank you.
Professor, wouldn't the for the product wouldn't the methoxide be on a wedge since
Oh,
it's
no, I
in
haven't changed the product yet. I haven't gotten there. Okay, so you have the charges going from the bromine, for the methoxide to make bromide. This is the transition. Oops, doesn't recognize those. I've never known why, but it's not that smart of a program. So that would be the transition state. We'll just put it there. Okay, now I got to change how this is drawn. Now we could draw this so it really looks nice and it looks like the inversion, but you know what? You just have to switch the chirality of the center relative to what's on it. You know, just have to make the opposite. That's what that is.
Oh, I thought we put a wedge on the methoxide.
Well, you got to invert this center.
Oh, sorry, a dash on the methoxide. Sorry.
Well, this is a solid wedge. You have to change it to a hashed wedge. So this is the overall reaction. Yeah, it's going to select everything on the page. Who knows why? When you click on the arrow, you're supposed to get that reaction, and somehow it has it all associated. Okay. Oh, so that I don't need anymore. That'll come down here. Let me draw this a little differently. I'll leave the top one up there. Okay, so it wouldn't be unusual to draw the reaction the way it is at the top left. But if I'm going to invert this, actually, I don't have a methyl there, so let's not have the methyl here. If I'm going to do the reaction, invert this, I can draw it this way too. The methyls change sides, as is the bromide as it became methoxide. So this molecule and this molecule are the same, right? We in agreement? Just pick one up and flip it left to right, flip it upside down, and the ether is going to be on the left, methyl on the right, of course, and the R is going to be in front instead of the back. Let's see. These two are enantiomers. These two are enantiomers, so this and this are the same.
I think you're missing the ME on the other side.
Where?
You fixed it, my fault.
Okay. Yeah, I mean, the methyl's implied, but we can put it there explicitly. Put it here explicitly. Okay. Everybody happy? Yeah, and this is kind of challenging. And when I ask you to draw something like this, there are a lot of places to take off points. And if you simply screwed up in the chirality of the transition state, it's going to be anything going to be a minor deduction as long as the overall picture is roughly correct.
Do we have to explain why we drew our graph a certain way? Like, do we have to say like why this is the transition state, or do we just have to draw it?
This when I ask students to do this, this is a pain in the butt to consider simply because the considerations of partial credit are challenging. I have to be fair on the partial credit and consistent with a huge range of answers. No, I'm not going to ask for any explanation in addition to that. I
Okay.
need to keep my sanity.
All right.
You're off the hook.
Sounds good.
Yeah. I mean, if I had 50 students, my exams would be quite different. I've always wanted to teach the same lecture, but had an honors section within it. I've never asked if that's practical. I have a feeling it's not. But, they would get a different test, different worksheets, a different recitation section to make it more challenging for them. I don't know how well that would work, but, I'm so close to retirement. Yeah, maybe I don't want to do that. I plan to retire in a year or two or 3 or 4. Hasn't been decided yet. I doubt if I'm staying beyond 75. Okay, Moshe, your hand is still up. You still have a question?
Yeah, Dr. Hammond. I was just wondering, we were looking at the SN1 energy chart too, and you were mentioning the stereochemistry. Would we need to because I know that there's like a racemic mixture of like near racemic of inversion and then retention of like the stereochemistry for SN1. Would we need to show that on the energy diagram if you were to go and ask
You
that?
don't have to go out of your way to show it in any great way. It's going to be implied by what you draw.
Okay.
So if I want to know if you actually understand that, it would be an easy separate question.
Okay.
You'd simply show the planar carbocation intermediate and attack from either side. It's an easy question. Dulce, you have a question? Your hand's still up.
Yeah, good morning, Professor. I just
Good
had
morning.
just on what we might see on tomorrow's exam. Are we like more likely, are we more likely to maybe see anything related to like addition reactions or like anything about redox reactions tomorrow, on Friday?
I'm not going to tell you what the question is, but the focus of the current period is E1, E2, SN1, SN2. Okay?
Yeah, so
And
any
we are going
yeah,
to have a future lecture or unit on a more comprehensive set of addition reactions.
okay. And in regards to like redox reactions as well, like will we see anything like that?
Yeah, well, we're not doing a lot of redox this semester, but you got to get used to the way organic chemists do it. Organic chemists rarely use oxidation numbers for atoms. We have our own way of looking at redox. Um, the only time we ever get deep in it is if we have to do a calculation to limit the reagent. Generally when we do an oxidation excess, we do a reduction excess, we're all happy.
All right, thank you so much.
Oxidation numbers are a huge pain to use in organic chemistry, so we avoid it whenever possible.
All right, thank you.
Yeah. I see Pablo in the chat has put up a reaction we haven't learned yet. If you've looked ahead to the reaction worksheet number 2, that's for the future. I posted them both at the same time, so I don't have to risk forgetting to post the other one. Okay, so it's the reaction worksheet number 1 where you need it. I mean, there's a lot on that second one you don't know, but it's not that far away. So it's there when you need it. I don't know, maybe something on that worksheet you've learned. I didn't check it, but I would just leave it alone now. User 1 again. That hand went away.
Yeah, hi, Professor. So we just like got introduced to acids and bases yesterday. I was wondering, can
I'm
we do?
sorry, you got to introduce them in high school,
Yeah,
probably, but certainly in
yeah,
Gen
we did,
2.
but not in like in so much detail. I was wondering, can we do a practice problem on that? Um,
Um,
like the kind that we might.
yeah, sure. Let me save this before I lose all my good work. Um, File, export. Okay, what do I already have? Trying to think if there's an easy way to not have you watch me do too many more. Give me a second to do a search. Okay, here we go. Yeah, I didn't post this. So I can do that. Okay, so look through these and see if you know which side the equilibrium is on.
So we look for the side with the stronger.
And if you want to, you can draw reaction arrows just for practice drawing reaction arrows.
Do we look for the side with the stronger acid or base? Is that how we
You have to
can?
recognize the stronger acid and base pair. Always they're up there, always a pair. And they are going to react, which means the side with the weakest acid and base are going to dominate.
The first one is going towards the products because of the negative charge on the oxygen, right? Because oxygen is have a greater
You
electronegativity.
got, if you just look at the base, hydroxide versus acetate, yeah, it's kind of a warm-up, isn't it?
Isn't hydroxide a stronger base?
Oh, yeah, absolutely. This is going to go 100% to completion to make the acetate.
Oh, so it's
Okay?
going towards the right side.
It goes towards the weaker base. And which is a weaker acid? I mean, which is a stronger acid? Acetic acid or water? It's acetic
It,
acid. Yeah.
so it's going towards the right. Okay.
Yeah. Yeah.
For
And
the second,
the second one is equally easy.
it's going towards the left
Yeah, chloride is
because
not a base, not in any normal conditions. HCl is a far stronger reaction than acetic acid. So yeah, these are kind of easy. What about this one? Now you got to think a little bit.
Is it equilibrium?
Nope, one side is favored. By how much I can't tell you. It's not going to be dramatically, but it's not going to be 50-50. So which acid is stronger? Or the better thing to look at is which carboxylate is more stable. Acetate is has a carboxylate. So is the chlorine going to help stabilize the carboxylate more, or is the bromine going to help more?
Is it favored to the reactants?
Yeah, again, let's focus on the reason.
Yeah, it's because of
Is
induction now.
chlorine going to have a larger inductive effect or bromine?
Mhm.
Which is more electronegative, chlorine or bromine? Electronegatively, electronegatively, electronegativity decreases as you go down a group on the periodic table. Chlorine is more electronegative. It is second place. Oh no, it's third place in most electronegative. Oxygen is slightly more electronegative. Okay, so if this carboxylate with the chlorine is more stable, means it's less basic, it means the right side will be favored.
Yeah, I have a question, Dr. Hammond. For
Sure.
I thought that it mentions in the textbook that with bromine and chlorine, if it's along the same column, electronegativity isn't what we base it off of. It's more of
No.
size.
You're confusing different things. You're confusing what the atom itself can carry with its inductive effect. So bromide
Oh,
is
oh,
inherently more
oh.
stable than chloride, although they both don't care really. But chlorine has the bigger inductive effect when it's influencing a nearby negative charge.
Yeah, yeah, I see where I
So
went wrong
yeah,
here.
that's fine. That's fine. We got that straight now. Okay, so everybody follow? Chlorine.
so
Yeah, go ahead.
so the base with the negative side and the chlorine is more stable.
This
That's why.
chlorine is capable of pulling more of the electron density out of this anion than the bromine is.
So that makes it a stronger base, or
The chlorine, the influence of the chlorine is to make this a weaker base because it's helping
oh,
with the negative charge.
oh, so it's making it a stronger acid and a weaker base.
This is a stronger acid because that's the weaker base. But the anion is usually what you want to look at and think about.
So which way is the arrow going again? Towards the right?
So if the chloroacetate, which is the name of that, monochloroacetate, is more stable, the equilibrium is going to favor the right. So on the right, we have the weaker acid and the weaker base. On the left, we have the stronger acid and the stronger base. There's not a huge difference, but there's only one structural difference, so that's going to determine whatever difference there is.
All right, so we would draw arrow towards the right. Okay.
Okay.
Thank you.
Dr. Hammond, I had a quick question.
Yeah.
For B, I know HCl is a very strong acid. However, if we're solely judging based on the anions, can we say that since Cl is a larger atom than O minus, it could carry the negative charge better?
I'm
Therefore,
sorry, I somehow lost you. Which line are we on?
oh, B.
B.
Since Cl is a larger atom, it could carry the negative charge better. Therefore, it's more stable, so it will float to the left.
Yeah. This one is just so extreme. I mean, you know, HCl is a strong acid. Acetate or acetic acid is a weak acid. I would just go with that.
Okay, thank you.
Yeah, I mean, the implication is the chloride carries that negative charge just fine. So, what you're saying is correct, but it's just not the most obvious to me. There's two ways to do this: compare the acids or compare the bases. In this case, I think the acids are what's going to be the most convincing. But your
For
argument for the basis is fine.
I see. Thank you, Dr. Hammond.
yeah, for B, it strictly goes towards the left.
Oh yeah, there is no equilibrium here, really. Yeah, the amount on the right here in number B is going to be approaching parts per billion, if not less. So there's no real equilibrium here. Okay, D should be another easy one. Which side is favored?
Does it go towards the left?
Yeah. These three fluorines have a great stabilizing effect on this anion. Trifluoroacetic acid was mentioned in lecture yesterday. It is making an attempt to be a strong acid. The chlorine on this beta-chloropropionic acid, give it a name, is helping just a little bit. It's not much more acidic than acetic acid. So this is an extreme comparison. The left is very highly favored.
And the right side has all the strong acids and bases.
This is a relatively strong acid, and that is, it's a castilic acetate, it's a weak base. Okay, E.
Dr. Hammond, quick question.
Sure.
Are we always to assume that induction would help stabilize an anion better than resonance, or just in this case because fluorine?
No, we're not seeing resonance here with carboxylic acids. We have resonance. Yeah, there's no resonance on here. We can make up some questions on that.
I have a
Oh,
question regarding
Yeah,
pKa.
this worksheet was actually made for my survey class I taught, my pre-nursing orgo. So it doesn't go into resonance.
I have a question for the pKa.
Yeah.
So how does the pKa influence the equilibrium here?
A pKa is just a reflection of how acidic something is. So we are doing a relative assessment of pKa. So this has a pKa of, I don't know, one-ish. This is going to have a pK of 5-ish. So when we say something is a stronger acid, we mean it has a lower pKa. Okay, let's do E and then I'll make up some.
E is towards the products.
The products. Does everyone agree? It's a weak acid and a weak base. And I actually talked about this yesterday.
Wait,
Acetic acid, I'm sorry?
wait, do you mean it goes towards the
No, I
well?
am simply observing that we consider acetic acid a weak acid. We consider ammonia a weak base.
Yep.
What I mentioned yesterday, acetic acid is a weak acid versus water. Ammonia is a weak base versus water. Combine them together, and this is going to be 99.9+% to the right. It's not an extreme, not really an equilibrium. There can be traces of the front of the ammonia and acetic acid, but only small traces. This is a very good acid-base reaction. Okay. So I don't think I'm going to post this again. It's intended for a lower level class.
Do you think Aereo is sufficient for tomorrow's questions, or should we really just memorize the
You
pKa?
need to know examples. Um, give you something that's a little more.
Professor, just a question. Just to confirm, the test is after tomorrow, not tomorrow, correct? Because I heard several people say it's tomorrow.
No. No, I have said nothing about Thursday. How can I have it on Thursday?
Okay, yeah, because I had just heard a couple of students when they were asking the questions, they said, "Oh, tomorrow's test." So I was just making sure.
Well, I hope they just misspoke. You know, yeah, I don't know where that would come from.
Okay, thank you.
Our exams are on Friday. I
After.
I think there is one student taking it at the testing center on Thursday, which I gave permission for. I don't know if that actually ended up that way or not. I don't mind an individual student or two taking a test early, especially if they have a solid reason, because they get to find my typos for me, I would hope. Okay, which is more acidic? Oh, I'm sorry. It's not quite what I intended. Trying to do two things at once here. Let's give you some practice with resonance structures while we're at it. Okay, which one's more acidic? Now it makes sense.
The one with the nitrogen?
Boy, you've written down all the resonance structures already? Okay,
No,
if you want to know which one is more acidic, were you guessing or you can give me a complete explanation?
maybe because like nitrogen is like electronegative, it's gonna pull the electrons. I was
But
thinking,
oxygen's electronegative. That's going to be involved on the left.
oh yeah, because that one
Yeah.
has both nitrogen and
Oh,
oxygen.
so the first thing that we need to settle is which is more acidic, means which of these two is more stable. So which one does resonance stabilize better? So this is as much practice drawing resonance structures as it is an acid-base question.
Oh, there's something on the chat.
Yeah, I had to change, I had to send my wife a text. I have to take my mother-in-law to the doctor today for a blood screening, so, and I have no idea when the appointment is. Okay, so you're going to have resonance structures going all the way through. So, oh, let me back up. Okay, you're going to have resonance structures going all the way through. So let me show you a shortcut to drawing all of them. Where is that symbol? Come on. Oh, it's here. There it is. So, um, so you have the negative charge there, and then it goes there and goes there. It's going to end up here, but it's also going to go up there. Same thing over here. There, there, there. So that's the phenoxide resonance that you've seen, but that's going to go up here. And so it's really the resonance structures at the end that will be the most important. Eat this thing. Should have gotten a higher end computer too. So hopefully you can draw all the intermediate resonance structures. I'm just going to go to the end. Oops, we both. Okay, so that is the resonance structures. The key, the key resonance structure. Okay, looks funny. Okay, so this is a teachable moment. Which is more stable, the structure on the left or the structure on the right? And I'm going to tell you it's the structure on the right. There's only one net negative charge here, and it's being shared by three electronegative atoms to some extent. Mostly the oxygens, of course. But the nitrogen's electronegative will have some influence. And positive and negative charges on neighboring atoms, even if they can't neutralize, are a pretty favorable thing. So a nitro group is a very good electron drawing group. It is one of the best you can put on an aromatic ring, both through induction and through resonance. That'll become very important next semester. But in terms of getting used to resonance and everything, it's not a bad practice problem. And there is something I don't understand that's somewhat favorable about this orientation. Double bond, this pair double bond, and this double bond. That has something going for it I have never really understood.
I have a question.
Mohammed, yeah, no, I just saw it in the text. The nitro group. This separation of charge is not a harm on the nitro group at all. It actually can't be neutralized. It has to be drawn this way. And it's a weakness of localized bonding. Okay, so it's not the same as drawing a carbonyl with two charges. This is, you consider one of these more of an isolated negative charge, but it's it resonates throughout the whole thing. So there's two oxygens and three carbons happen to carry this negative charge and this one too. So it's more the presence of the this grouping of the heteroatoms that is beneficial. So I can't explain completely why this isn't a big strike against the nitro group. It just isn't. So it's kind of something different.
So the molecule with the nitrogen is a stronger acid?
Yep.
So the more electronegative atoms we have, the stronger the acid tends to be because
Well,
of this.
Jim, let's not try to rationalize it because I can't explain it completely. Nitro groups are great electron dot groups. Yeah, I can look up the pKs of these if you want to. They're both going to be fairly acidic relative to the phenol. The resonance will help both of them, but the right one will be the clear winner. So file that away. There's something unique about nitro groups. They're really good at this.
And its
Yeah.
conjugate base is going to be really stable.
Let me phrase it this way. Okay. These charges should be considered more like an ionic bond. That's one way to come to terms with it. There's probably a more sophisticated answer, but ionic bonds are pretty good. And so this cluster here isn't so bad, especially when this one negative charge is only partly there, right? That negative charge is on four other atoms. And this negative charge is a natural part of a nitro group. Think kind of it's a decent ionic bond in this case. Okay?
Is that why you didn't use that oxygen's negative charge to do the resonance? Because it's technically an
Well,
ionic bond?
you can take this negative charge in the nitro group and do a resonance charge to this oxygen, which is hidden now. Okay. If I take away the label, I get the oxygen gone too. So this is the nitro group, and there's a resonance structure inherent in it. And so there's a half a charge on each oxygen in effect. Half charge is not really existing. It occurs simultaneously. A single negative charge simultaneously occurs on both oxygen being sharing it.
This acid, the strong acid, would easily lose a proton and become its
Well,
conjugate.
paranitrophenol is not a strong acid, but it's stronger than phenol.
Say if we had a reaction with that acid, it would definitely go forward, lean towards the forward, because it would easily lose a proton and become a conjugate base, I guess.
The pKa of phenol is 10. The pKa of paranitrophenol is 7. So it's a 1,000-fold increase. Para-acetylphenol is closer to 8. So the nitro group is 10 times as effective as an acetyl group in acidifying that. Yeah, I mean, I would not put those on a test for you to compare next semester, maybe. It's just a good practice at resonance structures, which we've now gotten into in a bigger way. And AI is useful for some things to find some things quickly if you have good judgment as to when to use it. Even for simple chemistry data, there are mistakes on the internet. So you always need to be cautious. Okay, I don't want this to go forever. I think you're about as ready as you're going to get for the acid-base stuff, other than, going through the slides and everything.
Hey, Professor, can I ask a question?
That's what we're here for.
Okay, so I wanted to ask, on the exam, are we gonna be seeing questions that will give us a product that is both like SN1 and SN1 and E1, for instance? Like if we're, you know how
Um,
sometimes we
for
can.
on an exam, except in the rare case when I ask for something more, you only need to put down the major product.
Okay.
If you put the minor product down, you'll get, generally, it depends on the question. But in general, if you do the chemistry correctly, but end up the minor product, I give you 2 out of 3. So a lot of
Okay.
partial credit chances on these reactions.
And can I also ask another question?
Absolutely.
Um, for this exam, will we see like bromination and chlorination or like halogenation or hydronation?
Free radical reactions? No.
Okay. Okay,
We,
thank you.
we are going to see some more free radical actions before the end of the semester,
Okay.
but that's not something I need to bring up now. Orgo tortures you enough. I don't have to help it.
Okay, thank you. And like, is there any topics that you want us to focus on from like the prior exams?
Um, okay, the one thing about sophomore organic chemistry, it's nominally a sophomore course, a 2-semester course.
Mhm.
The focus is on reactions and everything you need to know to be able to predict the reactions.
Okay.
And then there are the more minor topics, nomenclature, safety I speak to, right? But I don't test on it. Um, yeah, stereochemistry is important in its own right, but it's a
Right.
result of reactions.
Okay. So like when you say nomenclature, just understanding how to name them and stuff, right?
Yeah.
Okay.
And how do we see molecules to predict reaction products?
Mhm.
Well, mechanisms. And we focus on functional groups as defining the chemical products or the chemical properties of a compound. We
Right.
we did intermolecular interactions, and that was based on function groups and how they behave. We did addition reactions. That's how alkenes react. We're doing
Okay.
SN1, SN2, E1, E2, and that's how do alkyl bromides and related compounds react. It's
Okay.
all focused on reactions, but understanding them as well. That's where the mechanisms come in, where the energy diagrams come in. Okay.
Thank you so
So,
much.
so free radical reactions, I'm not going to bring up again until the final. Well, no, I'll have to see what the next exam has. I may have some on there because you're going to learn some new ones. But the simple free radical bromination, yeah, don't have to focus on that too much. But all the rest of the reactions, yeah, don't leave home without them.
Okay, sounds good. Thank you.
Teresa,
Um, Hello, Professor. I was just wondering how significant aprotic versus protic reactions will be like in regards to this exam. Like, will there be any instances where that will determine what the reaction is, like what the major product is?
um, it can make a difference. We learn that, but that probably would be more of a focused question to see if you understand that difference. But yeah, protic solvent. Let me explain this in a way I didn't do in lecture. Protic solvents will not help an alcohol that's protonated react faster. But if a halogen is ionizing, it's developing a negative charge. This is both in SN1 and SN2. They both have the halogen leaving somehow, and E1 and E2 as well. Whenever the halogen's a leaving group and you switch to a protic solvent, the bromine that's breaking its bond is developing a negative charge. And having hydrogen bonding around that developing negative charge on the halogen makes it a better leaving group. So better leaving groups favor unimolecular over bimolecular reactions, and protic solvents do, but it's really the same effect because the protic solvents make the halogens better leaving groups. So there are relationships between these things. We think of them separately, but they're kind of related. Okay?
But then
Thank
an
you.
then an aprotic solvent makes the leaving group a worse leaving group.
Well, it doesn't help.
So it would favor bimolecular.
Yeah, I mean, the halogens are more reactive in aprotic solvents because they're not hydrogen bonded. All these things are related. But for beginners, you can't really think of all these things at once, which is why we talk about how good the leaving group and we talk about protic solvents as different factors, because then you don't have to make that connection. Yeah, don't worry too much about it. I know this is very challenging material. The exam is a little shorter. It's 4 pages, not 5 pages. Do your best and let the curve take care of the rest. Go as prepared as you can. Ooh, I had all sorts of hands now. Omar, you went up first?
Yeah, I had a quick question. Could you go over how to do carbocation rearrangement for a ring?
Oh, absolutely. So the main ring that you're dealing with is a four-member ring. Three-member rings can do it too, but they become a four-member ring. It's not that big of an advantage. So we generally focus on a four-member ring. And so just where it belongs. Okay, let's do an example we haven't done. Let's put something on the ring to make it more interesting. Okay, excuse me while I mumble at ChemDraw. I always set the default to subscripts and it always turns it off. I don't know why. Okay, give me the product. Here's a reaction for you. A relatively challenging one in the current context.
Hydronium.
Hello? I couldn't figure out excuse me for a while. I had no idea what the noise was. My phone was buzzing because I turned off the ringer. Yeah, what do we know? So, yeah, can you send me the address and the text and remind me of the time? What time do you suggest I leave? Okay, I'll set my alarm for 1 o'clock. Okay, Yeah, ignore what I'm doing. I'm just trying to think through something. Okay, two problems you can go over. Make it look a little normal here.
Is the molecule in the arrow also known as H3O, or is it only if like if there's water here?
No,
Or could
there's no water here. This is concentrated sulfuric acid. So you're allowed to use sulfuric acid as your acid.
Question?
Yep.
For this type of question, if it's on the exam, do we just show the product or do we have to draw the entire mechanism?
Yeah, I mean, I can do both, either one, but there's no, well, there's no overt mechanism like this on the exam. Definitely will be on the fourth one.
Would we start off with the conjugate base deprotonating the OH?
And you got a very strong acid here. You start by protonating the OH. Sulfuric acid is one of the true strong acids. So this is going to be a carbocation rearrangement. Yeah, user one and Tasnim, are you waiting with a question? Your hand is up.
Oh, I had a quick clarification before, which is A products are only for E2 and SN2, and products are for SN1 and E1, and that's all we have to know about that.
For SN1, the weak nucleophile has to be a protic species because it has to lose the hydrogen to make a neutral product. For E1, E1 is not a very common reaction, but a protic solvent isn't necessarily needed. But we're not going to focus that much on the solvent. Solvents are something you learn more through experience. Um, just focus on the factors that you're learning and don't worry too much about solvent otherwise. Now, for SN1, the solvent is the nucleophile. So it's not just the solvent. That's why it needs to be protic.
Um, okay, and one more thing is SN1 cannot have a reaction with a secondary carbon, right? So if there's a secondary,
SN1 reactions do, in some cases, okay. Um, when you take a like secondary alcohol with con HBr, that works to make the bromide. And because it's a protic solvent with a good leaving group, it's an SN1 or a SN1 reaction. But solvolysis does not work. That's not considered solvolysis. Okay? We draw that on the side. Okay, you're going to protonate the OH. Water's a great leaving group. You're in a protic solvent. The solvent here is water. ConHBr means water. And you're going to get a carbocation, but you're under very strongly acidic conditions here. There's not much of the base that wants to promote it to deprotonate it. And bromide is a very good nucleophile in high concentration. So this is an exception to what you learn, and it works. So this is an SN1 of a secondary. Remember, there's an exception to everything you learn in orgo. But solvolysis only works with tertiary. This is not considered solvolysis.
Is this the only exception we should know for SN1?
Oh yeah, this is the only one. Absolutely.
Okay.
Wait,
It's pretty rare with secondary. And again, this is not considered solvolysis. And then there's another thing too. If you get some elimination, the HBr can add right back to it. And in this case, you get the same product, but in general, that wouldn't be the case.
So what if you have a secondary carbon with beta branching, and then you have like a weak nucleophile, weak base?
I'm sorry, what do you want to do?
You have a secondary carbon with beta branching,
With a
and then
bromine on it or
uh, whichever. I
a
mean,
leaving group?
yeah, and then you have a weak nucleophile, weak base reacting with it.
Um, if it's a weak base, elimination won't be a problem. If the weak nucleophile is good enough, you can get an SN2. But the SN2 will be slowed down. The more basic the nucleophile, the more the beta branching will hurt you. Okay, so acetate, probably going to work pretty well. What's in between? Cyanide, CN minus, you're going to get more elimination because it's kind of in between. It's not alkoxide, but it's not acetate.
Don't you want more beta branchings if it's basic?
Beta branching slows down SN2.
But it helps for E1 and E2.
Oh no, if you want elimination, it's not going to hurt you. This can be eliminated either way, depending on your choice of base. Okay, let's go through these. I don't want to go on too much longer because I'm going to get hungry and grumpy. Okay, you're going to protonate it. You're going to lose water. You're going to make that carbocation. Okay, and now you can shift from you can have this shift or this shift. Just a minute, the phone is ringing. Yeah, my mother-in-law got it. And this isn't a great example because you get two products here, right? The shift gives different products. They both leave. Is it? The carbon is shifting over, so this bond is going there. So that is where the cation is going to be. Yeah, let me check the phone.
Well, what type of reaction is this again? I don't remember doing this like in class.
Okay, this is going to give two products. I'm only going to do the one. Okay, so remember that's where the positive charge is going to be because that's where the electrons are shifting from. And so the shift going to erase that because this carbon down here is the one that's shifting over. The positive charge goes back here, right? And now make it into a more reasonable structure. Ooh, it didn't clean it up very well. It does not clean up rings well. Yeah, we'll do that. Okay, now concentrated sulfuric acid. What's going to happen next?
Wait, for the cation, wouldn't it stay there since that's like a tertiary spot, so it's like more stable?
No, the shift is no, the shift is driven by the ring strain. And so there's an advantage to the carbon shift because you're taking a cyclobutane and making a cyclopentane out of it. And now the next step is loss of a proton to give the alkene. Consulfuric acid dehydrates alcohols. And so you're going to protonate it, make this cation. These electrons are going to shift away from this carbon to that carbon, right? It has to be, you have to lose a bond to the neighboring carbon. This is the bond you're losing. So it's coming over and making this. And so this methyl is this methyl. This
Will
carbon got a new bond, it's this carbon. And then with consulfuric acid, it's just going to eliminate and make this alkene.
we'll get an example like this on the exam, right? A question like this.
I'm sorry?
Will we get a question like this on the exam?
It's certainly possible. This is part of the curriculum we've done. The one down here, I put on, it's easier, but it's got a little complication. So, just go through it. The same thing's going to happen to give a secondary cation. One of these two carbons will shift over as the major reaction route. Okay, so these electrons move over. The methyl goes with it. I'm going to draw it up here because it looks silly if you try to squeeze it in. And so that is what you get. And now this is going to eliminate. Again, we're in concentrated sulfuric acid. And you're going to get that alkene. Do you guys know why it's not going to make the tri-substituted? It's only going to make the di-substituted?
Resonance.
Resonance. It's in conjugation with the aromatic ring. So I can just bring that out by drawing it explicitly. So this pattern with this double bond, single bond, double bond is favorable. It's not hyperconjugation. It's just normal conjugation here. Okay, and we're coming up on 2 hours now. I'd like to cut this off, but if somebody has pressing last questions, I still have two hands up, but I don't know if that's intended. Mohammed or user one?
Professor, I just wanted to clarify one thing. For acid-base reactions, we always want to go from the strong acid and strong base towards the weak conjugate acid and the weak conjugate base.
Well, it's not what we want, it's what the chemicals want.
Yeah, like that's the direction of the preferred side. I don't know how to word it. So we would say that
Yeah,
it's going
the
towards.
equilibrium favors the weak acid and weak base.
Okay.
The students don't seem to like it as well as I do, but who's going to win? The strong acid or the weak acid? The strong acid is going to win, meaning it reacts as an acid. So the weak acid is more present. The strong acid gets its way. It gives up a proton. Students are not focused, seem not to be focused on the logic of it. They simply want to know which side to pick. I want you guys to understand it, and I know you're capable of it. You just need to change your attitude towards learning. Give up what they did to you in high school.
Dr. Hammond, I just have a question about the top example. Why like for the cyclobutane, why can't a hydride shift occur? Why does it have to be the methyl on the side?
If this hydride here shifts, you don't really make a tertiary cation because rings do not like sp cubed or sp squared carbons in them. It increases the ring strain. So you
Okay.
shouldn't consider that a normal or tertiary. Plus, you don't get rid of that ring strain. The ring expansion is kind of, oh, that was hard to hold small. I'm glad I'm five-member ring now. You know, it's a sigh of relief to the bonds in the molecule. Okay?
Yeah, I see
I can
that. Thank you.
anthropomorphize the chemicals. We do it all the time in Argo, don't we?
Yeah. Ugh.
The molecule prefers. I'm sorry, they're not thinking. They just are.
Dr. Hammond,
Yeah.
I promise to make it quick.
No, that's okay. It's not, as long as I'm getting successive meaningful questions, I can hang on even for another half an hour, although then I'm going to have to rush my lunch. I have to drive over to Terrytown across the Hudson River this afternoon.
I see. So if we have a tertiary carbon, right, and it's reacting with a weak base, weak nucleophile, but it's not giving us like a hint, like solvolysis or like heat at the bottom. How
Heat,
would we?
heat doesn't necessarily promote elimination. You got to be careful with that. Heat may just be necessary to get the molecule to react.
Hmm.
You know, it's not going to help you, but it's not necessarily the deciding factor. Um, I don't know if you were here at the very beginning. T-butyl bromide is a stable molecule. It has some reactivity. But if you put it in methanol and come back the next day, it won't have done much. You got to heat it to get it to react. Heat it until it's hot or heat it till it's warm. You still have to heat it a little bit. Then you'll still get SN1 as the major reaction. Okay?
But in general, right? How would we know if it like if we're acting with a weak base, weak nucleophile? How would we know if it's like going to be an E1 or SN1?
Yeah, same question.
Solvolysis only works if the nucleophile, the weakly basic nucleophile is the solvent. Like methanol's got to be the solvent. If it's a solvent, SN1 reactions are useful. If it's not the solvent, if you have a lower concentration, or if the solvent is a somewhat basic weak nucleophile, you're going to get elimination. And E1 reactions are not very common. They're not very well controlled. E1 are not common, but E1 is even less common. They're just not useful reactions. So if it's not the solvolysis, like just heating it, warming it up, warming it up is heating, right? If I say heat, it doesn't mean hot. You know,
Mm,
if it's 60 degrees in your house, you turn on the heat, so it's up to 68. It's not hot. Okay. So don't let heat drive it.
I see.
Okay. If I say reflux it, now you were talking hot.
Mhm. And ACO minus would that be considered like a good
It's
nucleophile
a
and
weak nucleophile, but it can't be the solvent. Sodium acetate is a salt. It's a solid. There may be some trick where you can do solvolysis with that, but you can just dissolve your alkyl bromide in acetic acid and do solvolysis. If you see acetate, yeah, you're going to wonder what the solvent is. And hey, it is a base. Acetate's a weak base, but a carbocation is actually a fairly strong acid. given the chance, right? It really wants to lose that proton. It'd be cute to see if somebody has determined an apparent pKa of that acid. It's not a true pKa because it's an equilibrium. It's not an equilibrium situation. But, carbocations, the protons that can eliminate are pretty acidic. So acetate is a bad choice. They probably give you mostly elimination. But it'd be an unusual thing to have.
I see. Thank you so much.
Yeah.
I just have one last question, Dr. Hammond.
I won't hold you to that.
Um, for the ring expansion, why does it go to the tri-substituted and not the tetra-substituted? Like the double bond? Why does that occur?
Oh, no, the cation I had is this, right? So it can't reach down here. It can be di-substituted or tri-substituted.
Yeah, wait, I kind of don't understand why can't it go?
The,
Oh, actually, I
the
do see it.
cation started here. So the proton lost has to be next to it.
Yeah.
It's not impossible you could have a hydride shift and then make the alkene. I mean, you could argue for that.
Could the double bond go somewhere else or
It's
only
always
in that spot?
possible
Okay.
if this cation persists, it can have a hydride shift to make tertiary, and then you can get down that. And some of these things give mixtures that's hard to control. Plus, if you just treat an alkene with acid, if you treated this alkene with a strong acid, a strong non-nucleophilic acid, there's some
Mm-hmm.
acids like perchloric acid, where perchlorate, the anion, is not a nucleophile. It's a terrible, terrible nucleophile. Um, so if you could protonate here, put the cation there, and then eliminate, conditioned to equilibrate alkenes. You can arrive at those conditions. But other than some esoteric study, why would you want to?
Okay.
Professor, for these reactions, I understand that we get a carbocation and the electrons move towards it. For the second part, how do we get the double bond again? Like, how's that happening?
Well, it's an E1. This reaction is essentially an E1 elimination. It's just as a rearrangement as an additional step. Okay. And there is no good base here. That's your base. Don't you dare use that unless there's a better choice. But that's the base here. So that is simply going to take away. Come on. Oops. That's simply going to pluck off that hydrogen. So it's an E2 elimination, but with additional rearrangement. Does that make sense?
Yes, sort of.
Yeah, I mean, you guys are beginners here. I didn't try to to write a hard exam. The hard comes by itself. I think the exam is quite reasonable. I don't think you'll be disappointed by it. Challenged by it? Sure, it's an orgo exam. But I think everything considered, you'll find it reasonable. And again, if I misjudge and the exam is harder than I think it is, the way I curve it takes care of that. The harder I accidentally make an exam, the more generous the curve will be. So don't stress out. Get prepared, get a good night's sleep on Thursday night, and come and do your best. That's all you can ever do.
Somebody asked earlier, I don't know if you answered it, but they said like is it better to use Oreo or to just remember the pKa?
Oreo, as I said in lecture, is not useful to make any decisions without a lot more understanding. In fact, I think the only usefulness of Oreo is to remember the four factors to assess. You just don't do A of Oreo. It's different, therefore I've made my decision. It's just not that simple. So you have to assess, what are they? Atom, resonance, induction, orbital. You have to assess all of those. And you kind of have to know how to balance out this thing. And I could give you questions where the comparisons are so challenging, I wouldn't know. I'm not going to give you that. Right? Again, Oreo, yeah, the only real usefulness for it is just to remind you what factors to check. Other than that, I consider it useless. Okay, and when I talked about acids and bases, I refer to them. We've learned that sp carbons are much more electronegative than sp cubed carbons, and therefore acetylenes, when they're terminal, are weakly acidic. We've certainly talked about resonance. We've talked about the atom. Thiols are considerably more acidic than alcohols.
Also, double and triple bonds tend to be more acidic
The,
because they're more.
the hydrogen on them, none of them are really acidic. You can't directly deprotonate a alkane or alkene other than on unusual conditions, but deprotonating acetylenes, that's pretty routine. And that's because of an sp carbon.
So a double bond has more S characteristics as compared to a single bond. So
Yeah,
among
the
double
sp
bond,
squared is 33% S, sp cubed is 25% S.
so more S characteristic means stronger acid.
Yeah, so I don't want to call the proton here acidic, but that anion would be more stable because of the hybridization of the carbon. I mean, deprotonating that directly is not a real thing. But that anion can be made indirectly. We'll learn about that next semester, early in the semester. Oh, somebody says we have a new mayor. Yes. Interesting result. I'm not allowed to take a political stance, but it's an interesting result. We live in far too interesting times, though. Okay, are we done? Okay,
Thank
so
you, Professor. Thank you.